But what if I take that blame and I multiply it by these weights? What do I get? I get a blame on x. I'm basically saying, how bad is x? And I can then add the learning rate times that blame to x. And what that does is it adjusts the inputs in a way that will reduce the difference between the y and y hat. So you can adjust both the weights and the inputs of your neural network. And if you do, then essentially y becomes the only thing that you need to look at. So y are actually your features. And since we usually use the letter x for features, we should probably call those x, and we should call this something else like state. We'll do that. Okay. Now, if you want to, you could adjust only the inputs. So you would still do forward propagation and back propagation, but you don't actually have to update the weights of your neural network, right? You could, if you wanted to, only update the inputs. What would be happening then if you did? You'd be asking the question, you'd be saying effectively, I know my neural network is good. I like the way it interprets inputs, but I don't trust that my inputs are right, so I can just adjust those inputs until I minimize my difference from my predicted values and my blame. Or if you wanted, you could update just the weights and not update the inputs. Or you could update the weights and the inputs and they could all morph together. You see how you could do all of that? And under various scenarios, those all make sense to do. Particularly in assignment 8, that's how we're going to train this model. Now, for historical reasons, these instructions have two sets. The first one is the one you're not going to do. The second one is the one you actually are going to implement. The reason I did it that way is I thought this first set was reasonably easy to understand, and then after you understand it, then we'll add a few more differences to adjust it. Basically, how can I explain this? Well, let me just walk you through the pseudocode and help you understand what it's saying. And when you understand what it's saying, that'll show you really how we're going to be training this neural network here. Okay, so imagine we have this model here. This represents the observation function of your neural network, or of your model. Yeah. I'm going to describe to you now how we're going to train the observation function. In other words, first we're going to train this part. Then after we're done, then we're going to train that part. Okay. So suppose we have x. X is our data. And notice there's only one matrix coming into our training method here. There's not two. There's not, here are the features and here are the corresponding labels. Now all we have is, here are some observations. As in, you get to watch the baseball player throw a pitch, or you get to watch the crane wander randomly through its space. You don't really get meaning for those x's, you just get observations. Okay? So let n be the number of rows. Let v be an n by k matrix. V is what I'm using to represent state here. I don't know why I called it v. Yeah, I do. It's because w is the weights and x is the features. So it made sense that v should be the next letter because you have v, w, and x that are just all in a row. No great reason. I just use v. Okay. To start with, we're going to set all the values in v to 0. In other words, for this, we've got this crane that's randomly walking through its state space. We're going to assume we don't actually know the state of the crane in any of these images. So we're just going to assign them all to zeros for right now. do a whole bunch of times. I used a double for loop. I have an outer loop of counts 10 times and an inner loop that counts 10 million times. Why? Because apparently I'm decaying my learning rate here. See how my learning rate gets smaller every time I do it? I don't want to do that 10 million times, otherwise my learning rate will be 0 way too quickly. I could have just as well decayed it by multiplying by 0.9999999 or something like that, but it was too hard to compute how it would go to. It's not hard to compute. I could do that just fine. I don't know why I did it that way, but I did. There you go. There's 2 loops. I'm saying here, T is a random row. So in other words, I'm going to pick a random observation from my set of observations. I have a sequence of observations of my crane wandering through its state space in random order. I'm going to pick one of them at random. Then I'm going to say my features, the inputs into my model, are this vector of states. Now remember, my vector of states was actually initialized to all zeros. So initially, this is garbage. These are the states that I don't actually know that I'm using to describe the frames in my video. And as this loop iterates, V is going to learn, V is going to converge to intelligent representations of the state of the system. Label, x sub t, this is the actual picture itself. These are the values from x. So it's a little backwards that I'm using my x as my labels. My observations are now my labels, but that's the way this neural network is set up. I would predict, this is the forward propagation step or the activation step. Then you compute the blame on the output units. You do back propagation to compute the error on the hidden units. Also compute the blame terms for the inputs. That is, I multiply by the weights on the very inputmost layer to get the blame on the inputs. Then I can refine the weights by gradient descent if I want to, and I can also refine V of t by gradient descent. So in other words, I'm updating the state of just that one frame. Does that make sense? I think I need to draw for you something. Imagine I have this model, and inside the model are the weights. But I have here V1, V2, V3, V4, V5, V6, ... And I also have here X1, X2, X3, X4, X5. Pretend that's an X. 6, ... If I randomly pick one of my X's, I'll pick X5. I'm going to feed in V5. And initially they're all zeros. But when I feed in V5 to try to predict X5, whatever blame I get is going to update both the weights and V5. Do you see that the weights are going to be updated for every single input vector and corresponding observation? Whereas each each state vector is only going to be updated with the corresponding observation vector. What's ultimately going to happen is the model itself is going to have to learn weights that work for everything. In other words, the model has to learn to map from any state to its corresponding set of pixel observations. But the state itself only has to appease the one observation. So we can actually update both of them, the weights and the inputs, and it's going to be meaningful because this is getting updated all the time, and this one's only getting updated for the one thing. I don't know if that came out very well. But what this forces it to do is the weights have to actually learn a mapping between state and observations, and the state only has to learn what it's supposed to be. Can you tell me how lost you are right now? Yeah.
What I don't understand about the state here is, okay, it'll generate a state, it'll generate the output, the X5, but how does the state have any meaning to us?
Aha.
A bunch of numbers.
That is a very insightful question. And the answer is it will not. And that's okay. So yes, we're going to end up learning a bunch of numbers that are latent. They only have intrinsic meaning to the model. So what's the point? Why should we even bother learning these numbers since we're never going to know what they mean? Let me show you something.
Like with the crane example, the numbers have a meaning of the position of the crane, I guess?
Yeah. These are actually the true states that I withheld from my system. Or this is a plot of the true states I withheld from my system. Now I started right here in the middle. You see green, but I actually plotted red. It's just that I started with red and then went through orange, yellow, green, blue, purple. I went through the spectrum. And as it happens, I wandered back into this region later on and covered up the red with green. But I started here, and you can see it's a random walk, right? I kind of just wandered arbitrarily through my state space and went whichever way my random number generator told me to go. So this is the true state. From each of these states, I generated a corresponding image. I trained my model only based on the images and knowing what action I had performed. I never told it what the state was. And then when I was done, my model had generated a bunch of intrinsic latent state representations. Let's look now at a plot of those meaningless intrinsic latent state representations. So here they are. In fact, let's zoom out so you can see them both at the same time. Okay. Do you see what's going on here? Now, I have green down in the bottom left corner, and there I have green in the top right corner. I have red in the top left corner, and there it's in the top right corner. So to align them, I have to take the images and flip them like that. And you can also see that the generated ones are kind of warpy in a strange way. Why? Well, why not? I mean, my model had no way of knowing that yaw and cable length were even orthogonal concepts. So it didn't put them on orthogonal axes. It has this arbitrary angular rotation there, and it's flipped two different ways, and it's warpy. So all of this is what the machine understood was going on when it took a look at the image. Does that make sense? And this is what was really going on when it took at the image. Who's right? Well, this is obviously right because it's true. This is the ground truth, right? You can't say this is wrong. But is the machine wrong? Kind of not. It depends on what you mean. But it's not wrong as long as we can accept that the machine is using its own metrics. Right? If these axes represent whatever the machine wants it to mean, and it happens to like nonlinear metrics, which we as humans hate. We like everything to be linear related. But as long as those numbers changing by a certain amount has meaning to the machine, I claim these numbers are actually right. And strangely, they are right enough that I was able to drive this crane around in my simulation thousands of time steps into the future, and it was still able to produce images that were visually in the right place compared to the crane, which is actually a lot better than a human can do. If I were to give you a sequence of actions, left, right, up, down, left, 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 right, 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 up, down, 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 left, 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 up, 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 right, 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 and you're trying to keep track in your head, okay, where's this crane going? You would not be able to nail exactly what's going on after some amount of time. Well, I was able to predict thousands of time steps into the future even while injecting Gaussian noise into both the transitions and the observations of the model, which shows that the machines actually, while these internal state representations look like they're warped and off and can't possibly be accurate, the thing is there's also warpiness and offness in the observation function that it learned to go with it. And when you put the two together, it was able to reconstruct very accurately what's going on in the system. Okay. So here's what you'll do in the assignment. You'll basically implement this pseudocode, except you won't. You'll really use this one instead. The only difference is this one does it 1 pixel at a time. See, I pick a random attention position and present it 1 pixel at a time, and yet it still works. So not only are we jumping around randomly, we're also looking at a random pixel through a straw, and somehow the system is still able to learn. And when you do that, you will get an accurate enough estimate of state, even though it's an internal representation of state that you can't understand, that you can use to train this transition function without having to do backprop through time. And in the end, your model of the whole system will enable you to build a simulator, and that's kind of the assignment. Does that make sense? Any questions? Yeah.
Would you like to talk about your type of layer?
Oh yeah, so how many layers do I use? I'm certain it's documented in here. I just don't know where. Layer. Make a 3-layer, there it is. 4 to 12 to 12 to 3 is what I did.
All the layers are linear? Or?
No. This implies each layer is a linear layer followed by a nonlinearity of the same size. And I use tan H for all of my nonlinearities. So this is actually 4 to 12 linear, followed by a 12 tan H, followed by a 12 to 12 linear, followed by a 12 tan H, followed by a 12 to 3 linear, followed by 3 tan H units. Okay, anyway, that's the assignment. I'm out of time, but do go get started on the assignment, and we'll talk more about it next time, and hopefully you'll have questions to give more meaning to the lecture.